In February of 2025, the James Webb Space Telescope quietly delivered a finding that the standard models of cosmology are not prepared to accept. Of 263 of the most distant galaxies it has ever imaged, 2/3 are spinning the same way. The odds of that being chance are about 1 in a million, and it is one fingerprint of a larger pattern that, the more you look, becomes harder to ignore. Stars spin, planets spin, black holes spin, even single electrons, with no measurable size at all, carry something we call spin. Tonight, we are going to ask why. Find your blanket, settle in, and let the universe quietly turn with us. Part 1. The pattern hiding in plain sight. In February of 2025, a paper landed quietly in the monthly notices of the Royal Astronomical Society. It was written by a computer scientist named Lior Shamir, working at Kansas State University, and it carried a finding that the standard models of cosmology are not prepared to accept. The paper examined 263 of the most distant galaxies the James Webb Space Telescope has ever imaged, in a region of the sky called the Jade Survey, and it asked a simple question of each one. Which way are you rotating? Clockwise, from our point of view, or counterclockwise? To ask that question carefully, you need extraordinary images, resolution on the scale of arc-seconds. You need to see a galaxy as more than a point of light. You need to see the curve of its spiral arms, the asymmetric shape of its disk, the subtle hint of which way that disk is turning relative to us. Until the launch of the James Webb Space Telescope in December of 2021, that kind of resolution was not available for galaxies at the highest redshifts. The Hubble Space Telescope, for all its achievements, could see the galaxies, but could not always resolve their rotation. JWST changed that. With its 6.5-meter primary mirror operating in the infrared, it could pull the shapes of galaxies that existed when the universe was less than 1 billion years old into focus for the first time. Shamir's analysis was one of the first systematic attempts to use those new shapes to answer one of the oldest questions in cosmology. The answer should have been close to 50-50. The universe, according to 100 years of established cosmology, has no preferred direction. Galaxies form in all orientations. Their rotations should be as random as coin flips. About half clockwise, about half counterclockwise, with only the small statistical wobble you would expect from any honest sample of 263 things. That is not what the data showed. 2/3 of those galaxies were spinning the same way. Just 1/3 were spinning the other way. And here is the part that makes the standard cosmologists uneasy. The further back in time the galaxies sat, the more distant, the closer to the Big Bang, the more lopsided the split became. If you take the youngest universe we have ever observed, billions of years before our own solar system formed, you find an early cosmos in which there appears to be a direction of spin. The odds that a sample like that comes out randomly, by chance, from a universe with no preferred direction are about 1 in a million. Astronomers do not, as a rule, dismiss 1 in a million coincidences. Now, perhaps that finding will turn out to be a measurement artifact. Perhaps the way the universe is moving relative to certain background radiation is brightening certain galaxies and dimming others, and we are seeing a selection bias rather than a real lopsidedness. There are several proposed innocent explanations, and you will hear me lay them out carefully later tonight. But here is what I want you to sit with at the beginning. 2/3 of the most distant galaxies we have ever seen are spinning the same way. Whether that turns out to be illusion or reality is one of the most consequential open questions in modern physics. And it is a question about something so basic, so ordinary, that I would bet you have never given it more than 10 seconds of thought in your life. Why does everything spin? Not just galaxies, not just stars, everything. The Earth turns, The moon turns. The sun turns. Jupiter and Saturn rotate so fast that they bulge at their equators. Asteroids tumble. Comets spin. Pulsars rotate at speeds that beg a belief we will get there. Black holes spin, and many of them rotate at very near the maximum rate the laws of physics allow. And once you go below the level of any of those objects, into the realm of atoms and particles, you find that even something as small as an electron, a thing so tiny it has no measurable size at all, a thing that physicists believe is a true point in space, carries with it a property that we call spin. Spin built into it, intrinsically, with no way to remove it, no way to stop it, and no way for the universe to be the universe without it. Stillness, it turns out, is the rare condition. Motion is the default. The universe rotates at every level we are equipped to measure, from the largest assembly of galaxies down to the most fundamental constituents of matter, and we do not have a single unified answer for why. We have several partial answers. We have a master principle that handles the bookkeeping of how spin moves between objects. But the question of why there was spin to begin with, why the universe is so persistently in motion, that question is still open. And the more carefully you ask it, the larger it becomes. It is one of those questions that hides in plain sight precisely because it is so obvious. A child might ask it and be brushed off with a one-line answer about the Big Bang. A high school student might ask it and be told something about angular momentum and figure skaters. A first-year physics undergraduate might ask it and be handed Noether's theorem. And at each level, the answer feels like enough. The questioner walks away satisfied. But every one of those answers is incomplete. Every one of them, when pushed on properly, opens out onto a larger question. By the time you have pushed all the way down, you find yourself sitting with the most difficult version of the question, which is this: why is rotation a property of the universe at all? Not how it is conserved, not how it is transferred, but why there is any of it to begin with. This is the question we are spending the next 2 hours with. So get comfortable, find your blanket, settle in. Tonight, we are going to take a journey from the smallest spinning thing in the universe, a single electron with no size, no surface, and yet a real and measurable angular momentum all the way out to the largest possible scale, the universe itself. We will pass through planets and stars and dying neutron cores. We will visit galaxies and the gigantic dark matter halos that surround them. We will look closely at black holes, because black holes are nature's most extreme rotators, and we will see how their spin literally drags the geometry of space-time around with them. And by the time we reach the final part, we will be sitting with the most provocative idea in modern cosmology, the idea that our entire universe might be a rotating object inside another, larger one, and that everything we have ever seen spin is the gentle inheritance of that primordial turning. I am not going to oversell that. Some of what you will hear tonight is published, peer-reviewed, established physics. Some of what you will hear is published speculation that mainstream science treats with great caution. I will be careful with you about which is which. But the question itself, the simple, almost childlike question, why does everything in the universe spin, turns out to be one of the few questions in physics where the more carefully you look at it, the stranger the universe becomes. The textbook answer is a beautiful conservation law you learned in school. The answer beyond the textbook is something else entirely, and we have years, not decades, before we know which one we are living in. So consider this the night we sit with the question gently and patiently, and let it carry us where it wants to go. The first stop is the principle that ties all of it together, the same humble piece of physics that makes a figure skater speed up when she pulls her arms in. That explains why a neutron star can rotate 43,000 times a minute, and that hides at the bottom of every spinning thing we will visit. That is where we begin. And the chain of questions it sets up is the chain that will pull us, by the end of the night, all the way out to the edge of what physics can currently say, is less than break time equals 1s, is greater than number, part 2. What spin actually means. To understand why the universe spins, you have to first understand what spin actually is. And to understand what spin actually is, you have to understand the single most important conservation law in physics that almost nobody outside of physics has ever heard of. It is called the conservation of angular momentum, and it is the reason your morning coffee swirls when you stir it. It is the reason the planets all orbit the sun in the same plane and the same direction. It is the reason a spinning bicycle wheel will hold itself upright when a stationary one would topple. It is the reason every galaxy we have ever observed is shaped the way it is shaped. It is, in a very real sense, the rule that organizes the universe. Angular momentum is what you get when you take an object's regular momentum, its mass times its velocity, the quantity that measures how hard it is to stop something moving in a straight line, and add to it the question of where the motion is happening relative to some chosen point. You multiply by the distance from that point. The further out the motion is happening, the more angular momentum it carries. The faster the motion, the more angular momentum. The heavier the moving thing, the more angular momentum. It is, in equation form, the radius times the mass times the velocity. Or, in slightly more sophisticated terms, the radius vector crossed with the linear momentum. But the equation is not the point. The point is what the equation does. What the equation does is refuse to change. If you have a system that nothing outside is pushing on, nothing outside is twisting, physicists call this an isolated system, then the total angular momentum of that system stays exactly the same forever. It cannot increase. It cannot decrease. It can move around between pieces of the system. It can be exchanged between objects that touch or pull on each other, but the total stays fixed. It is one of the most rigidly enforced rules in all of physics, and it has been verified to extraordinary precision in every experiment that has ever been done. The classic demonstration is the figure skater. You have seen this. She begins her spin with her arms stretched out, turning slowly. She has some amount of angular momentum set by however hard she pushed off the ice. Then she pulls her arms in, and she speeds up. Not by pushing on anything, not by adding energy, just by pulling her mass closer to her axis of rotation. The radius part of the equation shrinks. To keep the angular momentum the same, the velocity part must grow. She has no choice. Physics does the arithmetic. This little observation, made by a child or by a physicist, is the kernel of how almost every spinning thing in the universe came to spin as fast as it does. Because the universe is, at its bottom layer, a place where things collapse. Clouds collapse into stars. Stars collapse into compact remnants. Material falls into the gravitational wells of black holes. Galaxies build themselves out of infalling matter. And every time something collapses, the same trick the figure skater performs is performed by gravity on a much larger scale. The radius shrinks. The angular velocity must rise to compensate. Whatever rotation was there to begin with, however faint, however nearly nothing, it gets amplified. Sometimes by factors of thousands, sometimes by factors of trillions. Let me give you a worked example of how absurd the amplification can become. Suppose you have a cloud of hydrogen gas that is 1 light-year across roughly 6 trillion miles, and which is rotating at the leisurely rate of 1 revolution per 10 million years. That is so slow you would never notice it. A clock placed at the cloud's edge would record a motion of less than a centimetre per second. It is barely rotation at all. Now suppose this cloud collapses, by gravity, into a star roughly the size of our Sunday, the The Sun is about 1 million miles across. The collapse factor is around 6 million. Conservation of angular momentum demands that the angular velocity goes up by the square of that factor, which is about 36 trillion. The new rotation rate is the old rate times 36 trillion. 1 revolution per 10 million years becomes 36 trillion revolutions per 10 million years, which is roughly 1 revolution every 9 seconds. The star, if all the angular momentum of the original cloud were retained, would spin extraordinarily fast. In practice, our Sun has shed most of that angular momentum into the protoplanetary disk and into the solar wind over its lifetime, which is why it now rotates only once every 27 days. But the principle is the same. Even a whisper of rotation in the original cloud becomes a real and measurable spin in the object that condenses from it. This is why a star spins. This is why a galaxy spins. This is why your planet spins. We will look at each of these stories in detail, but all of them are the same story underneath, and the underneath is conservation of angular momentum. So the next question is, why is angular momentum conserved? And the answer to that, when you find it, is one of the most beautiful pieces of mathematics in the entire history of physics. It was proved in 1918 by a German mathematician named Emmy Noether, working in Göttingen, and her result is now called Noether's theorem. It is one of the few theorems in physics that is actually used in everyday research by working physicists every single day. Noether's life is worth a brief pause, because the theorem and the woman who proved it are connected. She was born in 1882 in Erlangen, the daughter of a mathematician. She wanted to study mathematics herself, which in late 19th century Germany was very nearly forbidden to women. She attended lectures, when she was permitted to, only with the express permission of each professor. She completed her doctorate in 1907. Then for 7 years she taught at the University of Erlangen without pay, because German law did not allow women to hold faculty positions. David Hilbert and Felix Klein, two of the most influential mathematicians of the era, eventually persuaded the University of Göttingen to admit her as a Privatdozent, an unsalaried lecturer, and at one of the meetings of the faculty senate, where her appointment was debated, Hilbert reportedly exclaimed, "I do not see that the sex of the candidate is an argument against her admission. After all, we are a university, not a bathhouse." She did much of her most important mathematical work during those years. The theorem that bears her name was proved in the same year, 1918, that Einstein's general theory of relativity was being absorbed by the physics community, and it provided the mathematical foundation that made the energy and momentum properties of general relativity make sense. She emigrated to America in 1933 after the Nazi rise to power, and she died, far too young, in 1935 at the age of 53. Noether's theorem says that every conservation law in physics is the reflection of a symmetry of nature. If a thing in the universe stays the same when you do a certain operation, then a certain quantity has to be conserved. The two ideas are mathematically equivalent. They are different ways of saying the same thing. Energy, Noether showed, is conserved because the laws of physics do not change with time. The experiment you do today gives the same result as the experiment you do tomorrow, and that fact, surprisingly, is what forces energy conservation to hold. Linear momentum, the kind of momentum that explains how a billiard ball keeps moving in a straight line, is conserved because the laws of physics do not change with location. The experiment you do here gives the same result as the experiment you do across the room, and angular momentum is conserved because the laws of physics do not change with direction. The experiment you do facing north gives the same result as the experiment you do facing south. Space, in other words, has no preferred orientation. That symmetry is what we mean when we say space is isotropic, and it is what makes angular momentum a conserved quantity. I want you to sit with that for a moment, because the implication is doing more work than it looks like. If the universe truly has no preferred direction, then nothing can spontaneously start spinning out of nothing. Spin cannot appear from a system that previously had none. Any rotation you see, anywhere, must have come from somewhere. Either it was always there, or it was transferred from somewhere else. There is no third option. The law refuses one. So now, finally, we can begin to ask the question we came here to ask. Imagine, for a moment, a single cloud of gas in the early universe. A thin, cold, almost still expanse of hydrogen and helium drifting somewhere in the dark, perhaps a light year across. That cloud has some net rotation. It is not zero. It cannot be exactly zero, because in any region of space, there are always small asymmetries, pressures from one side that do not quite match the pressures from the other, gravitational pulls from neighboring clouds that do not perfectly cancel. The cloud has a faint rotation, a breath, a drift, nothing you would notice, but not nothing. Then gravity begins to pull it together. The cloud begins to collapse. Its radius shrinks. The conservation law steps in and demands that the rotation speed up to compensate. If the cloud's radius shrinks by a factor of 10, the rotation has to be 100 times faster. If by a factor of 1,000, then 1,000,000 times faster. By the time the cloud has shrunk by a factor of 10 million, which is what happens when a cloud the size of a light year collapses into a star, the original whisper of rotation has been amplified by a factor of 100 trillion. This is the bottom story under every spinning object in the universe. Every star, every planet, every solar system, every galaxy, they all rotate because the cloud that fed them rotated, even by a tiny amount, and gravity did the rest. Conservation took care of the bookkeeping. But here is the question that is going to drag us by the hand for the rest of the night. Where did that initial whisper of rotation come from? The cloud got its rotation from the larger cloud it was part of. That larger cloud got its rotation from the galaxy's interstellar medium. The galaxy got its rotation from somewhere too. Each step backwards, the rotation has to be inherited from a larger source. And each step backwards we can in fact identify until we get to the very largest scale of all, to the universe itself. And at that scale, the question we have been asking quietly, child to adult, becomes a question that physics cannot yet answer with certainty. We will follow that chain, link by link, all the way to its end. But first we need to see what conservation of angular momentum actually does, in the wild, when gravity is given hundreds of millions of years, and an enormous mass of gas to work on. So let us start where every textbook starts. Let us start where our own bodies came from. Let us start with the cloud that became our solar system. Is less than break time equals 1s is greater than number. Part 3. How the solar system got its spin. 4.6 billion years ago, in a quiet region of the Milky Way, an enormous and freezing cloud of gas began to collapse. We do not know exactly what tipped it over the edge. The leading theory is that the shock wave from a nearby supernova, a dying star, perhaps a few hundred light years away, passed through the cloud and compressed it just enough that gravity took over the rest of the job. Another possibility is that the cloud was disturbed by the passage of another star. The actual cause is lost to time. What we know is that the cloud, having been roughly in equilibrium for hundreds of millions of years, was pushed across a threshold, and once across that threshold, it had no way back. The cloud, before its collapse, was something like 1 light year across. That is roughly 6 trillion miles. Inside it, there was hydrogen and helium left over from the Big Bang, mixed with trace amounts of heavier elements that had been forged in the cores of earlier stars and scattered through space by their deaths. The mixture was almost uniform, almost still, cold enough that the molecules barely moved against one another. And then it began to fall. The collapse was not symmetric. No collapse in nature ever is. There were lumps, there were faster-moving regions and slower-moving regions. There was that small but non-zero net rotation the cloud had carried from its parent environment for as long as it had existed as a coherent cloud. And as the radius of the cloud shrank, the conservation of angular momentum did its work. The whisper of rotation amplified. As the cloud's diameter went from a light year down to half a light year, its rotation rate quadrupled. From half a light year to a quarter, 16 times the original rate. From a quarter to an eighth, 64. The amplification compounded. By the time the cloud had collapsed to a fraction of its original size, it was spinning hard enough that something had to give. The cloud had begun as roughly spherical. Now centrifugal forces, really. The inertia of the rotating matter pulled the cloud's equator outward while the poles continued to fall in. The sphere became an oblate sphere. The oblate sphere became a thick lens. The thick lens flattened, over hundreds of thousands of years, into a thin and rotating disk. At its center, the densest, hottest concentration of matter began to glow. Hydrogen fusion ignited. The sun was born. Astronomers call the disk that formed around the young sun the protoplanetary disk. We have now imaged hundreds of these disks around other young stars, with telescopes like the Atacama Large Millimeter Array in Chile. They look almost shockingly similar to one another. A central star, surrounded by a flat, rotating disk of gas and dust, often with gaps in the disk where planets are quietly being assembled. The first time astronomers got a truly high-resolution image of a protoplanetary disk was in November of 2014. The Atacama Large Millimeter Array, known as ALMA, pointed at a very young star called HL Tauri, only about 1 million years old, in the constellation of Taurus, about 450 light-years from Earth. The image that came back was one of the most consequential photographs in the history of astronomy. It showed, in unmistakable detail, a perfect rotating disk around HL Tauri, marked by a series of concentric dark gaps. The gaps were the orbital lanes that planets were already, at 1 million years of age, beginning to clear out of the disk. We were watching, in real time, the formation of a new solar system, and the disk was rotating in exactly the way our theoretical models had said it should, flat, oriented around a single axis, with the central star at the center. The image confirmed that the story we had been telling ourselves about our own solar system's origin was not just a theory. It was a process we could watch happening, today, around other young stars. Inside our own protoplanetary disk, the assembly began. Microscopic grains of dust, drifting in the disk and sharing its motion, collided gently and stuck. 2 grains became a clump became a pebble. Pebbles, given a few million years and a great deal of gravity, accreted into boulders, into mountains, and into bodies large enough to gravitationally pull in their neighbors. By the time the disk was a few tens of millions of years old, what had started as smooth gas and dust had been swept into hundreds, then dozens, then finally just 8 major bodies, the planets each carving its own gap in the disk and clearing its own orbital lane. And every one of those planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, was born of the same rotating disk, which means every one of them inherits the same direction of motion. They all orbit the Sun in the same direction. They all orbit close to the same plane, what astronomers call the ecliptic, and almost all of them rotate on their own axes in the same direction too. This is not a coincidence. This is conservation of angular momentum, writ across an entire solar system. The Sun itself rotates. It takes about 27 days to complete one rotation at its equator, and a little longer near its poles. That differential rotation is what generates the Sun's magnetic field, which in turn drives sunspots and solar flares and the 11-year solar cycle, but those are stories for another night. The point for our purposes tonight is that even the largest and most massive object in our solar system, the Sun itself, holding 99.8% of the mass of the entire system, is rotating because the cloud that made it was rotating, and the radius of that cloud collapsed by an enormous factor. Now, the story would be too tidy if there were no exceptions. And here is where it gets interesting, because the exceptions in our solar system are not random. They tell us something subtle about how conservation of angular momentum works. Venus is the first exception. Venus, our nearest neighbour and the second planet from the Sun, rotates the wrong way. Most planets, viewed from far above the Sun's north pole, rotate counterclockwise. Venus rotates clockwise. Its axial tilt is 177 degrees. That is essentially upside down, and it does so very slowly. A single Venusian day one rotation of the planet takes 243 Earth days. That is slower than Venus's own year. The Sun on Venus rises in the west and sets in the east, very, very gradually. How does this happen? It cannot have come out of the original rotating disk. The disk would have given Venus the same prograde rotation as every other planet. Two main explanations are taken seriously. The first is that sometime in Venus's youth, perhaps within its first few 100 million years, it suffered a giant impact, a collision with a Mars-sized body that struck it at exactly the wrong angle. That kind of impact could deliver enough angular momentum, opposite to Venus's existing rotation, to flip it. The second explanation involves Venus's extraordinarily thick atmosphere. Over billions of years, solar gravity and tidal forces acting on a planet with that much atmospheric mass can gradually slow and reverse its rotation, especially when the rotation is already slow. It is also possible that both contributed. Whichever explanation is right, the underlying point is the one I want you to take away. The total angular momentum of the solar system is still bookkept. Venus's lost rotation went somewhere. It got transferred into the Sun, into other bodies, into orbital motions, into the kinetic energy of the impacting body that struck it. The total never changed. The same conservation law was watching. Venus just lost the local lottery. There is also a more subtle effect on Venus that is worth pausing on, because it tells you something general about how rotation interacts with atmospheres. Venus has a carbon dioxide atmosphere, about 90 times as massive per unit area as Earth's. That much air, sitting on a slowly rotating planet, develops global circulation patterns that pull on the planet's surface through friction. Over billions of years, the atmosphere can act as a brake. Indeed, Venus's atmosphere actually rotates around the planet much faster than the planet rotates around its own axis. The upper atmosphere completes one circuit of Venus every 4 Earth days, while the planet's solid body takes 243. This phenomenon is called superrotation, and it is unique to Venus among the rocky planets. Why does the atmosphere spin so much faster than the surface? The honest answer is that we are not entirely sure. There are leading theories involving the deposition of angular momentum from solar heating, but the question is still open. Even in our own solar system, even on our nearest planetary neighbour, the details of how angular momentum is moved around are matters of active research. Uranus is the second exception, and it is even stranger. Uranus is tipped on its side at 97.77 degrees. Its axis of rotation is almost parallel to the plane of the solar system. Uranus rotates like a barrel rolling around the Sun, rather than like a top spinning. As a result, Uranus has the strangest seasons of any planet for 42 years. One of its poles points almost directly at the Sun and bakes in continuous daylight, while the other pole sits in continuous darkness. Then the situation reverses. The most likely explanation once again, is collision. Probably with one Earth-sized protoplanet, possibly with two, in the chaotic period when the outer solar system was still settling down. The impact transferred enough angular momentum in the right direction to knock Uranus permanently sideways. And then there is the Earth, which spins once every 24 hours on an axis tilted 23.5 degrees from the perpendicular of its orbital plane. The tilt gives us seasons. The rotation gives us day and night. The combination gives us the climate patterns that shaped every civilization that has ever existed. None of these conditions would obtain if the Earth did not rotate. The Coriolis force, which deflects fluids in motion on the rotating planet, drives the global wind patterns, the trade winds, the ocean currents that warm Europe and cool Peru, the hurricane spirals that always rotate counterclockwise in the northern hemisphere and clockwise in the southern. Without Earth's spin, none of this exists. The story of life on this planet is, in a real sense, the story of life on a moderately tilted, moderately fast-spinning rock around a moderately small star, and almost nothing about that story would be recognizable if any one of those properties were different. It is worth lingering for a moment on how the Earth got its specific spin. The leading explanation for the formation of our moon is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized body, sometimes called Theia, after the mother of the moon in Greek mythology, collided with the proto-Earth at a low angle. The impact ejected an enormous quantity of debris into orbit around the surviving body. That debris, also rotating, coalesced over what may have been less than 1,000 years into the moon. The collision dramatically affected the Earth's rotation rate. Just after the impact, our planet rotated once every 4 to 6 hours. Days were short. The moon was much closer to the Earth than it is now, and the tides it raised were enormous. Over the 4.5 billion years since, the tides between Earth and moon have transferred angular momentum from Earth's rotation into the moon's orbital motion. The Earth has slowed from a 6-hour day to a 24-hour day. The moon has receded from its original close orbit to its current average distance of about 238,000 miles, and it continues to recede at roughly 3.8 centimeters per year, about the rate at which your fingernails grow. The angular momentum has been carefully traded between bodies, conserved to within the precision of any measurement we can make throughout the whole of Earth's history. The day is longer now because the moon is further away. But our story does not stop with planets. Because what we have just described, a cloud collapsing, a disk forming, gravity sorting matter into bodies that share a common rotation, is small potatoes by cosmic standards. To see conservation of angular momentum truly pushed to its limit, we have to follow what happens when a much larger object collapses much more violently. We have to follow what happens when a massive star runs out of fuel and its core falls inward, not over a few 100,000 years, but over less than a single second. And what gets born from that collapse is one of the most extreme objects in nature. So extreme that the figure skater analogy we have been working with stops sounding like an analogy and starts sounding like a description, is less than break time equals 1s, is greater. Number, Part 4. The Pulsar Limit Case. A star of 40 solar masses lives fast and dies hard. Through most of its life, it burns hydrogen into helium, like our own Sunday. But because of its enormous mass, gravity at its core is so intense that the fusion proceeds much faster than the Sun's. The star may live for only a few million years. Then it runs out of hydrogen and begins fusing helium into carbon, and then carbon into oxygen, and then onwards through neon, magnesium, silicon, all the way to iron. Iron is the end of the road. Fusing iron into heavier elements does not release energy. It absorbs energy. So once the core of the star has converted itself to iron, The fusion that has been holding the star up against its own gravity for millions of years simply stops. There is nothing left to burn. And in less than a second, the core collapses. The iron core, before the collapse, is roughly the size of the Earth. That is about 13,000 kilometers across. It collapses to a sphere about 20 kilometers across the size of a small city. The radius shrinks by a factor of about 100 million. The volume shrinks by a factor of more than 10 to the 24th power. And conservation of angular momentum, doing what it always does, takes the rotation rate of the original iron core and amplifies it by the same enormous factor. The core, before collapse, was rotating perhaps once every 20 days, in the gentle way the innermost interiors of stars tend to rotate. After collapse, that 20-day rotation has been compressed by a factor of 100 million. The new object, the neutron star at the center of what used to be a giant star, can rotate hundreds of times per second. The fastest one we have ever found is called PSR J1748-2446 AD. It was discovered by Jason Hessels, working at McGill University, on the 10th of November in 2004. It sits inside a globular cluster called Terzan 5, about 18,000 light-years from Earth, and it rotates 716 times every single second. Let me give you that number again, because the human brain does not naturally accept it the first time. 716 revolutions per second, 42,981 revolutions per minute. A car engine, redlined, tops out around 8,000. A jet turbine, screaming at maximum power, hits maybe 20,000. PSR J1748, a neutron star with twice the mass of our Sun, packed into a sphere the size of Manhattan, is turning at 43,000 revolutions a minute. The surface of that neutron star, at its equator, is moving at 1/4 the speed of light. That is roughly 75,000 kilometers per second. If you could somehow stand on the equator of PSR J1748 AD, and you cannot, because the gravity would crush you into a smear thinner than a sheet of paper, before you finish the thought, time on your wristwatch would run measurably slower than time on a watch in our laboratory, about 1 part in a million slower. Special relativity, in action, on the surface of an object you can spell out. Theorists have calculated where the limit lies. If a neutron star rotates faster than about 72,000 revolutions per minute, the centrifugal force at its equator exceeds the gravitational force holding the star together. The star, in that case, tears itself apart. PSR J1748 AD, at 43,000 RPM, is spinning at about 60% of the breakup limit. How does a neutron star wind itself up to that speed in the first place? The answer is interesting in its own right. Most isolated pulsars actually slow down over time because they radiate energy in the form of beams of light and gravitational waves, and that radiation carries angular momentum away. The young hot neutron star, left over from a supernova, might spin 100 times per second to start with, and over millions of years, its rotation will slow to once every few seconds, then once every minute, then ultimately to a stop. But a small fraction of neutron stars are in binary systems with ordinary stars. The companion star spills mass onto the neutron star, and that infalling mass, already carrying its own orbital angular momentum, spins up the neutron star like a flywheel. After tens of millions of years of accretion, the neutron star can be wound up to extremely high speeds. PSR J1748 AD appears to be one of these recycled pulsars, spun up by a companion that may have already been entirely consumed. Pulsars also have a quieter contribution to the story of cosmic rotation. The very fastest pulsars are, in a sense, the most extreme demonstration of conservation of angular momentum that nature has ever performed for us. They show, in real time, that the law we have been tracking is not a textbook approximation. It is enforced by physics with no margin for error, all the way out to the edge of where matter can sustain itself. That is the most extreme rotation we have ever measured. A star that has been compressed into a city, spinning fast enough that its surface flirts with the speed of light, sustained by nothing more exotic than the conservation of angular momentum and the very real possibility of its own destruction. I bring this up not as a curiosity, although it is a curiosity. I bring it up because it makes a point that I want you to keep with you for the rest of the night. The same boring law that makes a figure skater speed up when she pulls her arms in is the same law that makes a neutron star turn 43,000 times a minute. There is no special pulsar physics. There is no neutron star magic. Take the cloud collapse story we told for the Sun and turn the collapse dial all the way up. Make the radius factor 100 million instead of 10,000. And what you get, automatically, with no additional ingredients, is a city-sized object spinning at a quarter the speed of light at its equator. Conservation of angular momentum, taken seriously, accounts for the full distance from a quietly rotating cloud to one of the most extreme objects in nature. If a single dying star can be made to spin this fast by collapse, then the question gets larger. What about 100 billion stars? What about a galaxy is less than break time, equals 1s, is greater than number. Part 5. How galaxies got their spin. A galaxy is not a single object. A galaxy is 100 billion stars, plus enormous reservoirs of gas and dust, plus an even larger amount of dark matter, all held together by their mutual gravity and arranged into a structure that, in most cases, is shaped like a thin disk. The Milky Way is one of those disks. From above, it would look like a flat spiral, about 100,000 light-years across, with arms curving outward from a central bulge. Inside that bulge sits the supermassive black hole called Sagittarius A star, weighing about 4 million times the mass of our Sunday the Milky Way rotates. Our entire solar system is in orbit around its center. The Sun, sitting about 26,000 light-years out from that center, is moving at roughly 220 kilometers per second. That is around 500,000 miles per hour. At that speed, one complete orbit around the galaxy, what astronomers call one galactic year, takes about 225 million years to complete. The dinosaurs lived through less than one full galactic year of the Sun's existence. The Sun has completed only about 20 galactic years since its formation. Earth, despite carrying its weather and its civilizations, is, in galactic terms, on its 20th lap. We are, in a sense, very young. Now, where did the Milky Way's rotation come from? The cloud collapse story works for stars and solar systems. Does it work for galaxies? The answer is more interesting than a simple yes. At the scale of a galaxy, the cloud collapse story is replaced by a related but more nuanced one called tidal torque theory. It was developed by Fred Hoyle in 1949 and refined over the following decades by Jim Peebles, Sergei Doroshkevich, Simon White, and others. And it goes like this. In the very early universe, matter was distributed almost uniformly. Almost. There were tiny fluctuations in density, small regions that contained a hair more matter than average, and small regions that contained a hair less. These fluctuations were imprinted on the universe in its first moments, probably during the period of cosmic inflation, when the universe expanded by an enormous factor in a tiny fraction of a second. The fluctuations were unimaginably small at first, less than 1 part in 100,000, but they were enough. Over the next few 100 million years, gravity worked on those small overdensities. Regions with slightly more matter began to attract more matter from their surroundings. They grew. Regions with slightly less matter were emptied even further as their gas was pulled into the growing overdensities. The universe became lumpy. The cosmic web, The network of filaments and walls and voids that we see today when we map galaxy distributions began to take shape, and here is the part that matters for our question. A region of overdensity in the early universe was not a perfect sphere. It was an ellipsoid, stretched, by chance, slightly more in one direction than another. The neighboring overdensities, each of which had its own irregular shape, exerted gravitational pulls on it. But because the region was not a sphere, those pulls did not cancel each other out perfectly. They exerted a torque. They twisted the region. For about 400 million years, the angular momentum of each proto-galactic region built up linearly with time as the surrounding tidal field continued to torque it. Then the region reached what astronomers call turnaround the moment, when its expansion stopped and its collapse began. From that point onward, the same conservation law we have been tracking all night took over. The region collapsed, conserving its angular momentum, and what came out of the collapse was a dark matter halo, rotating with a characteristic dimensionless spin parameter that astronomers call lambda, equal to about 0.04. That number is shockingly universal. Almost every galactic-scale dark matter halo we have ever simulated or measured has roughly the same lambda. Different galaxies, different histories, different epochs, and the same spin parameter, give or take. It is the universe's signature in the rotation of its largest gravitationally bound structures. Inside each rotating dark matter halo, gas began to fall in. Hydrogen, helium, traces of heavier elements. The gas radiated away its energy by emitting light, which let it cool, which let it sink further into the gravitational well of the halo. But the gas could not lose its angular momentum the same way it lost its energy. Angular momentum was conserved. So the gas settled, not into a sphere, but into a disk. The same physics that flattened the protoplanetary nebula into a disk, scaled up by a factor of 1 trillion or so. And within that gigantic rotating disk, stars formed and clusters formed, and the spiral structure we see in the Milky Way and Andromeda and millions of other galaxies took shape. So when you look at a photograph of a spiral galaxy, you are looking at conservation of angular momentum at the largest scale where it has ever been imaged. You are looking at the same physics that made the Earth-Moon system, and the same physics that made our solar system, scaled all the way up to encompass 100 billion stars. A peculiar and quite beautiful detail. Within the cosmic web, the enormous network of filaments connecting galaxy clusters, the spin axes of galaxies, are not random. They tend to align with the long axis of the filament they sit inside. In other words, the cosmic web has a sort of handedness. The filaments are spinning highways, and the galaxies along them rotate around the highway, like beads turning around a wire. This was first noticed in detail in the 2010s by groups working with surveys like Sloan Digital Sky Survey. The mechanism is still being worked out, but it appears to be a natural consequence of how matter flows along the filaments during cosmic structure formation. And one more thing about galactic rotation before we leave it behind, because this one is important. When the astronomer Vera Rubin spent the 1970s carefully measuring how fast galaxies actually rotate at their outer edges, she found something that did not fit. The stars in the outer parts of galaxies were rotating just as fast as the stars near the center. By the laws of gravity, that should not happen. If most of a galaxy's mass were concentrated in its visible center, then the outer stars, like outer planets in a solar system, should orbit more slowly. They do not. They orbit faster than they should. Much faster. Either Newton's laws of gravity are wrong, or there is a great deal of invisible mass in galaxies that we cannot directly see. The second answer turned out to be the consensus. We call that invisible mass dark matter. We still do not know what it is, but we know it is there because the rotation of galaxies told us it was. The single property that has guided our entire video tonight, conservation of angular momentum, did not just shape galaxies. It also opened the door to one of the largest mysteries in modern physics. Rubin's discovery was, at the time, extraordinarily hard to accept. The idea that most of the matter in the universe is invisible and made of something we have never directly detected sounded, in the 1970s, more like science fiction than science. But Rubin's measurements were careful, and other astronomers reproduced them, and over the next 2 decades, the evidence accumulated from completely different directions. The motions of galaxies inside clusters, the way gravitational lensing bent light around galaxies and clusters, the patterns of fluctuations in the cosmic microwave background, every line of evidence pointed to the same conclusion. About 85% of the matter in the universe is something other than the protons, neutrons, and electrons that make up everything we have ever held in our hands. The remainder, the visible part, is the part we have spent 4,000 years building physics around. The hidden part dwarfs it. And the way we found out is that galaxies rotated too fast. There is something almost philosophically remarkable about that. Rotation, which sounds like a banal property of objects, ended up being the thing that revealed to humanity that most of the universe is invisible. The question we are asking tonight, why does everything in the universe spin, is the same question that, when asked carefully enough, told us that almost everything in the universe is hidden. So now we have the textbook story complete. A faint rotation in a primordial cloud, amplified by collapse, stars, planets, neutron stars, galaxies, all sharing the same underlying mechanism, the same humble law at every scale. The same answer to the same question, scaled across 30 orders of magnitude. But there is a hole in the textbook story, a hole that the textbook does not usually point out. The whole story depends on there being a primordial something, a cloud, a filament, an overdensity that already had some rotation in it. The textbook explains how that rotation gets amplified. The textbook does not explain where the original rotation came from. And to answer that question, we have to go somewhere stranger than any place we have visited yet. We have to go below the level of clouds and stars and galaxies altogether. We have to go to the level of matter itself. Is less than break time equals 1s is greater than. Number, Part 6. Quantum spin and the floor falling out. In the early 1920s, physics was in a strange and exciting period. Quantum mechanics, as a coherent theory, did not yet exist. Niels Bohr had a model of the atom that worked for hydrogen and almost nothing else. Spectroscopists across Europe were collecting more and more evidence that electrons inside atoms were doing things that classical mechanics could not explain. And buried in the data, becoming harder and harder to ignore, was an embarrassing little puzzle. Electrons inside atoms were behaving as if they had angular momentum that had nothing to do with their orbits, which was impossible. An electron, in the ground state of a hydrogen atom, has no orbital angular momentum. None. By the rules of Bohr's model, it should have 0 angular momentum altogether. And yet, experiments kept finding that it had angular momentum anyway. Something inside the electron, something not associated with its motion around the nucleus, was acting like a tiny rotating object. The decisive experiment came in 1922, in Frankfurt, at the hands of 2 physicists named Otto Stern and Walther Gerlach. They wanted to test whether atoms had any inherent magnetism. They built an apparatus that fired a beam of silver atoms through a non-uniform magnetic field. The magnetic field was designed to push atoms in different directions, depending on how their magnetic moments were oriented. If silver atoms behaved like classical tiny magnets pointing in random directions, the beam should emerge from the apparatus as a smeared band, many directions, many deflections, a continuous distribution. There is a famous story about the Stern-Gerlach experiment that is worth telling. Stern and Gerlach had set up their apparatus, fired their silver atoms through it, and tried to image the result. They could see, faintly, that the beam had split, but the image was unclear. Stern was a heavy smoker. He took a long pull on his cheap cigar one with so much sulfur in the tobacco that it was almost like burning a chemistry kit, and exhaled onto the detector plate. The sulfur from the cigar smoke combined with the silver on the plate to form silver sulfide, which is black, and which suddenly made the splitting of the beam clearly visible. Two distinct dark spots, with nothing between them. The discovery of intrinsic angular momentum, in other words, was made visible by a chemist's accident and a smoker's habit. Stern always credited his cigar as a co-author of the result. The beam did not smear. It split into exactly two distinct spots, not three, not a continuous band, exactly two. That result was, depending on how you describe it, either deeply confusing or quietly devastating. Whatever was inside a silver atom that was responding to the magnetic field, it could orient itself in only two discrete ways, up or down, with no in-between. The two-spot result on the detector screen behind the apparatus could not be reconciled with any classical picture of magnetism, of rotation, of angular momentum. There was something inside the silver atom that was quantized, and whatever it was, it carried angular momentum. In 1924, the Austrian physicist Wolfgang Pauli, working through these puzzles, proposed that the electron itself must carry an additional, intrinsic property, a kind of internal angular momentum that had no analogue in classical physics. Pauli was cautious about giving it a name. He called it a two-valued degree of freedom. Two younger physicists, Samuel Goudsmit and George Uhlenbeck, took the next step. They proposed that the electron literally spins on its own axis, like a tiny rotating ball, and that this rotation is what produces the magnetism that the Stern-Gerlach experiment had detected. They called it spin. It was a wonderful, intuitive name. But it was almost immediately clear that it could not be literally true, because the electron, in every experiment that has ever been done, behaves like a point particle. It has no measurable size. Modern experiments place an upper limit on the electron's radius of something less than 10 to the minus 18 meters, which is 1/1000th the size of a proton. And it may well be exactly zero. A point, a genuine mathematical point in space. A point cannot rotate. Rotation, in the geometric sense, requires extent. There has to be something that is offset from the axis, that is being carried around the axis. A point has no offset. There is no surface to spin. There is no equator. There is no axis. And yet, the electron, despite having no size, demonstrably and reproducibly carries angular momentum. It interacts with magnetic fields as if it were spinning. The mathematics that describes its behavior is mathematically identical to the mathematics of a rotating object. The experiments demand it. The theory demands it. But geometrically, it makes no sense. For a few years, physicists tried various rescues. Perhaps the electron had a tiny, finite size after all. Perhaps the spin was a literal rotation of charge distributed across a small electron volume. The calculations did not work. If you tried to model the electron as a small ball of distributed charge, rotating fast enough to produce the observed angular momentum, the surface of the ball would have to be moving faster than the speed of light. That was a non-starter. Goudsmit and Uhlenbeck themselves tried to withdraw their proposal when this difficulty was pointed out to them. Their mentor, the Dutch physicist Paul Ehrenfest, refused to let them. He had already submitted their paper for publication, and he told them that, even if the literal picture of a spinning ball was wrong, the underlying property they had discovered was real, and the name they had given it was good. Sometimes, a useful concept survives the failure of the picture that motivated it. The resolution came from Paul Dirac in 1928, with one of the most beautiful equations in the history of physics. Dirac was trying to write a wave equation for the electron that respected Einstein's special theory of relativity. Schrödinger's equation, which had been developed in 1926 and which is still what undergraduate physics students learn, did not include relativity. Dirac wanted an equation that did. When he finally wrote one down, the Dirac equation, which is now considered one of the central achievements of 20th century physics, the equation had two surprises baked into it. The first was that the equation predicted spin automatically. Spin was not something Dirac had to add by hand. It came out of the mathematics as a necessary consequence of combining quantum mechanics with relativity. If you wanted both, you got spin. You did not get a choice. The second surprise was that the equation also predicted antimatter. Each solution of the Dirac equation for the electron had a partner solution that looked like an electron with opposite charge, what we now call the positron. Dirac was initially uncomfortable with this. But 4 years later, in 1932, Carl Anderson found the positron in cosmic rays, and Dirac's surprise was vindicated. Antimatter was real, and spin had been there in the equation all along. What we learned from Dirac is that spin is not a behavior the electron does. Spin is a property the electron is. It is built into the relativistic structure of matter at the most fundamental level we know. The universe, if it is going to be both quantum mechanical and consistent with special relativity, must contain particles that carry angular momentum even when those particles have no extent in space. There is no other way for the mathematics to work. And here is the part that even now, almost a century after Dirac, sounds slightly insane until you sit with it long enough. Spin is quantized in units of 1/2 of Planck's reduced constant, which physicists write as 1/2. Every electron, every quark, every neutrino, all the fermions, the particles that make up ordinary matter carry spin 1/2. To bring an object that carries spin 1/2 back to its original quantum state, you have to rotate it through not 360 degrees, but 720, 2 full turns. If you rotate an electron 360 degrees in any direction, the electron's quantum state acquires a minus sign. It is, in some fundamental mathematical sense, upside down. You cannot see this directly. The electron looks identical to how it started, but if you put it into an interferometer alongside another electron that you have not rotated, the two electrons interfere destructively because of the minus sign. The experiments have been done. The minus sign is real. To get the electron back to its actual original state, with no minus sign, you have to rotate it through 720 degrees. 2 full revolutions. Now, this is a genuinely odd statement, and it deserves a moment. There is a famous demonstration of the same mathematics in everyday objects, called the Dirac belt trick, or in some traditions the Filipino wine dance. Take a belt, or a long flat ribbon, hold one end fixed in your left hand. Now twist the other end, 1 full turn 360 degrees, and try to remove the twist without releasing either end. You cannot. The twist is stuck. Now twist the end a second time in the same direction. The belt now has 2 full turns of twist. By moving the loose end around your body without rotating it, you can remove both twists at once. The belt becomes untwisted. The geometry of three-dimensional space, considered carefully, has this property. Single rotations and double rotations are topologically different. A double rotation can be undone by a path through space. A single rotation cannot. The Dirac equation forces electrons to live in this strange geometric regime where 720 degrees is the natural unit of return, not 360. In other words, the spin of an electron is geometrically real. It just lives in a geometry that is not the geometry your intuition expects. Down at the level of fundamental particles, even the everyday meaning of a complete rotation is something the universe quietly amends. Let me ground this in scales, because the scale comparisons are how you make the next leap. The angular momentum carried by a single electron in standard SI units is roughly 5 times 10 to the minus 35 joule-seconds. That is a 5 with 35 zeros in front of the decimal point. The angular momentum carried by the rotation of the Earth is roughly 7 times 10 to the 33 joule-seconds. The difference between those two numbers is about 68 orders of magnitude. The smallest spinning thing in the universe and the rotation of the planet you are standing on are not on the same scale of motion. They are not even on the same conceptual map. The difference between the electron and the Earth is far greater than the difference between the Earth and the entire observable universe. And yet, they are the same word. They are both called angular momentum. They both obey conservation. They both contribute to the total spin budget of the universe. They are both encompassed by the same theorem, Noether's 1918 result, that angular momentum is conserved because space looks the same in every direction. There is one more thing about quantum spin that I want to give you, because it does work that nothing else can do. Pauli, working through the implications of spin in the 1930s, eventually proved the theorem that bears his name and Fiers's. It is called the spin statistics theorem. It says that particles divide into exactly two camps, according to whether their spin is a half-integer or a whole integer. Particles with half-integer spin electrons, quarks, neutrinos, all the fermions, obey what is called the Pauli exclusion principle. No two of them can ever occupy exactly the same quantum state. Particles with integer spin, photons, gluons, the carriers of the fundamental forces, obey the opposite rule. They can pile up in the same quantum state in any number. That sounds dry. Stay with me, because the consequence is not. The reason atoms have structure is the Pauli exclusion principle, which is, fundamentally, a consequence of spin. The reason the periodic table has the shape it does is the Pauli exclusion principle. The reason solid matter is solid. The reason your body has volume. The reason a table holds up a cup of coffee. The reason your hand does not pass through the chair you are sitting on right now is the Pauli exclusion principle, which is, fundamentally, a consequence of the spin of the electrons inside ordinary matter. To see how this works, think about an atom. An atom has a nucleus at its center, surrounded by electrons in what physicists call orbitals. Each orbital is a kind of quantum mechanical region around the nucleus where an electron can be found. Each orbital is characterized by a set of quantum numbers, a kind of address. Now here is the rule. Because electrons are fermions, with spin 1/2, no two electrons in the same atom can have the exact same address. They must differ in at least one quantum number. The first two electrons in any atom occupy the innermost orbital, with their spins pointing in opposite directions, one up, one down, so that they differ in their spin quantum number. After those two, the next electrons must move to a different orbital, further from the nucleus. The next two move further still. The structure of the periodic table, the columns and rows, the chemical families. The reason carbon has 4 valence electrons and oxygen has 6 and noble gases are inert is a direct consequence of how electrons must arrange themselves around nuclei, because no two of them can share an address. And the reason no two of them can share an address is that they carry half-integer spin. Take spin away from the electron, even hypothetically, and the universe would have no chemistry at all. Every electron in an atom would collapse into the innermost orbital. Atoms would have no shell structure, no bonding, no molecules, no biology. Spin is the property that builds the periodic table. Spin is the property that makes chemistry possible. Spin is the property that allows a universe with chemistry to also contain things that breathe and think and watch sleep videos about cosmology. The fact that the universe contains stable atoms, that the universe contains chemistry, that the universe contains chairs and bodies and stars is a consequence of an intrinsic property called rotation in particles that cannot rotate in any classical sense. I want you to sit with that. The universe seems to insist on rotation at its most fundamental level, so insistent that it amends the geometry of three-dimensional space to permit it. So insistent that it makes solidity itself, the property of having a body, the property of being a thing, depend on the rotation of point particles that have no spatial extent. There is no obvious geometric reason this should be the case. The universe could, in principle, have been built out of point particles that did not carry spin. There would still be matter, in some abstract sense, but there would be no atoms as we know them, no chemistry, no biology, no chairs, no listeners. The fact that any of this exists is, at the bottom, because electrons turn in a geometry that requires 2 revolutions to complete 1 cycle of return. We started this video by asking why everything in the universe spins. We followed the answer from clouds collapsing to galaxies, talking to dying stars, rotating at the edge of breakup. At every step, the story was geometric. There were causes, there were transfers. Spin moved from one object to another, conserved, accounted for, bookkept. Down here, in the fundamental basement of physics, the geometry of rotation breaks, and rotation survives anyway. Whatever spin really is at this level, it is more fundamental than the geometric idea of turning. It is something the universe insists on, even when the universe has to invent new mathematics to permit it. Rotation is not a property of objects. Rotation is a property of matter itself. And that fact, more than anything else, is what makes the question of why the universe spins so much larger than it looks. We are now going to take this idea and ride it upward. From the electron, the smallest spinning thing, all the way up to the most extreme spinning thing in the cosmos, to the objects in which rotation becomes so intense that it warps space-time itself, to black holes. And from there, finally, we are going to ask whether the universe itself spins, is less than break time equals 1s, is greater than number, part 7, black holes and the Kerr universe. Every astrophysical black hole we have ever measured rotates. Not most of them, all of them, and many of them rotate at very near the maximum rate the laws of physics allow. The reason is the same one we have been tracking all night. Black holes are formed by collapse, massive stars collapse, stellar remnants merge. Material accretes onto already existing black holes. Each of these processes brings angular momentum with it, and once that angular momentum is delivered to the black hole, it is locked in. A black hole is, almost by definition, a place that things fall into and do not come out of. Whatever spin those things bring in, the black hole keeps. The result is that the universe's most compact objects are also, almost without exception, its most extreme rotators. The mathematics of a rotating black hole is more difficult than the mathematics of a non-rotating one. The non-rotating case was solved by Carl Schwarzschild in 1916, only months after Einstein published The General Theory of Relativity. Schwarzschild was a German artillery officer on the Russian front of the First World War. He wrote the solution from the trenches, sent it to Einstein, and died of a rare skin disease 3 months later. The Schwarzschild solution describes the simplest possible black hole, a non-rotating sphere of pure gravity. It is beautiful in its simplicity, and, as it turns out, it has very little to do with any real black hole that actually exists in the universe. The rotating case took another 47 years to solve. Roy Kerr, a New Zealand mathematician working at the University of Texas, published it in 1963. The Kerr solution is mathematically much harder than the Schwarzschild solution, and physicists had begun to suspect that a closed-form solution did not exist at all. Kerr found it. And what he found was not just an equation. It was a new piece of geometry. The Kerr black hole has an event horizon, like the Schwarzschild black hole. Inside the event horizon, nothing, not even light, can escape. But the Kerr black hole has something the Schwarzschild black hole does not have. It has an ergosphere. The ergosphere is a region of spacetime that sits outside the event horizon in a roughly ellipsoidal shape, in which space itself is being dragged around the rotating black hole, and the dragging is so violent that nothing inside the ergosphere can stay still. There is no possible trajectory, no possible engine power, no possible amount of energy that can keep an object stationary inside the ergosphere relative to a distant observer. The fabric of space itself is rotating, and anything within it is forced to rotate with it. This phenomenon has a name. It is called frame dragging, or the Lentz-Thirring effect, after two Austrian physicists who predicted it from general relativity in 1918, and it is not limited to black holes. Every rotating mass drags spacetime around with it. The Earth itself drags spacetime as it rotates. The effect is extraordinarily small for an object of Earth's mass and rotation rate, but in 2011, a NASA satellite called Gravity Probe B confirmed it directly. The satellite, in polar orbit around the Earth, was equipped with the most precisely machined gyroscopes ever built, nearly perfect spheres of fused quartz, polished to within 40 atoms of being perfect. The gyroscopes were set spinning, and their orientations were monitored over a year. The orientation shifted, very slightly, by exactly the amount Einstein's theory predicted. The Earth, by the simple act of rotating, was dragging the local spacetime around with it, and the gyroscopes were responding. If a planet's modest rotation can drag spacetime, then a black hole's extreme rotation drags spacetime extraordinarily. Inside the ergosphere of a Kerr black hole, the dragging is so complete that the local definition of standing still becomes rotating with the black hole. The geometry of space itself participates in the spin. Rotation is no longer a property of things sitting in space. Rotation is a property that space is. It is worth dwelling on the strangeness of that statement. In our ordinary lives, rotation is something objects do, and space is the inert background within which they do it. A spinning top sits on a table, and the table sits on the floor, and the floor sits in a stationary room. The top is doing the rotating, the rest is stationary. General relativity, in the presence of a rotating mass, denies that picture. The room itself, the table itself, the floor itself, the very fabric in which the top is rotating, is also being twisted. For an object as gentle as the Earth, the twisting is far too small to feel, far too small to notice in any everyday way. Around a rotating black hole, the twisting is loud. It is the geometry. It is everywhere. And once you understand that frame dragging is real, that the rotation of a mass alters the structure of the space around it, the simple question of what makes a planet spin starts to become a much harder question. The planet is spinning, but so, slightly, is the space the planet is in. And both of those facts have to be accounted for together by the same conservation law and by the same theory of gravity. In 1969, 6 years after Kerr published his solution, the British mathematical physicist Roger Penrose realized that the ergosphere of a Kerr black hole could be used to extract energy. The trick, in principle, is this. Lower an object on a rope into the ergosphere. While inside, split the object in two. Throw one half into the event horizon along a trajectory that goes opposite to the rotation of the black hole. The other half, by conservation of energy and angular momentum, must come back out of the ergosphere with more energy than the original object had. The extra energy is paid for by the rotational energy of the black hole, which slows down a little. This is now called the Penrose process. It is one of the few mechanisms in nature by which energy can be extracted from gravity itself by tapping into the rotational kinetic energy of a black hole. In principle, up to 29% of a maximally rotating Kerr black hole's mass energy can be liberated this way. Compared with chemical reactions, where you extract about 1 part in a billion of the mass energy of the reactants, or nuclear fission, where you extract about 1 part in 1,000, the Penrose process is extraordinarily efficient. It is, after matter-antimatter annihilation, the most efficient energy source the laws of physics permit. Whether nature actually performs the Penrose process on its own, we are not sure. There are mechanisms by which the rotation of supermassive black holes might be tapped to power the relativistic jets that astronomers see emerging from the centers of active galaxies. The Blandford-Znayak mechanism, developed in 1977, suggests that magnetic fields anchored in the accretion disk around a rotating black hole can extract rotational energy from the black hole and channel it into the jets. We see those jets. Some of them are millions of light-years long, blasting out of the centers of galaxies at very near the speed of light. The energy they carry has to come from somewhere. The rotation of supermassive black holes is the leading candidate. The Blandford-Znayak mechanism works, in rough outline, like this. Around a rotating black hole, especially a supermassive one with an accretion disk, magnetic field lines get threaded through the ergosphere. The field lines are anchored, far away, in the disk. As the black hole drags space-time around with it, the field lines are forced to rotate with it. The rotating field lines then act like the rotor of an enormous electric generator. They produce enormous electromagnetic forces along their length, which can accelerate charged particles outward from the black hole at very near the speed of light. The result is a jet channeled along the black hole's spin axis that can be remarkably narrow and remarkably long. In some galaxies, such as M87, the jet stretches a measurable distance outward. The energy budget is enormous, far more than the gravitational potential energy of the falling matter could supply. The only place such energy could come from is the rotation of the black hole itself. We are watching, through the most powerful telescopes humans have ever built, the rotational energy of a black hole being radiated across intergalactic space, transmitted as a fingerprint of spin into the wider universe. Now, how do we know that real black holes rotate? 2 ways, mostly, both extraordinary. The first is by careful observation of how matter falls into them. Material, falling into a rotating black hole, orbits in a manner that depends on the spin parameter. Astronomers call it A/m of the hole. For a non-rotating Schwarzschild black hole, the innermost stable circular orbit sits at 3 times the Schwarzschild radius. For a maximally rotating Kerr black hole, depending on which direction the orbit goes, the innermost stable orbit can be as close as half the Schwarzschild radius. By measuring the shape and temperature of the inner edge of an accretion disk around a black hole, astronomers can work backwards to the spin parameter. For Sagittarius A star, the supermassive black hole at the center of our own galaxy, the inferred spin is somewhere around 90% of the maximum allowed by the Kerr solution. For M87's supermassive black hole, the one famously imaged by the Event Horizon Telescope in 2019, and again in 2022, the inferred spin is similarly high. The actual photograph, the Event Horizon Telescope, produced that orange ring with the dark shadow in the middle encodes information about the black hole's spin. The asymmetry of the ring, the brightness on one side compared to the other, carries the fingerprint of frame, dragging in the immediate vicinity of the event horizon. The second way we know black holes rotate is gravitational waves. When 2 black holes merge, they emit a burst of gravitational waves, ripples in spacetime that propagate outward at the speed of light. The LIGO and Virgo and Cagra observatories detect these waves on Earth, and from the detailed shape of the signal, the masses and spins of the merging black holes can be extracted. As of the 4th observing run, which ran from 2023 to 2025, and which reached its 200th detection in March of 2025, the catalogue of black hole mergers is large enough to draw statistical conclusions about astrophysical populations. The signal of a black hole merger has 3 stages, and each one carries information about the spins. The first stage is in spiral. The 2 black holes orbit each other, gradually drawing closer as they radiate energy away in gravitational waves. The frequency of the signal during in spiral encodes the masses of the 2 holes. If the holes are spinning, their spins induce a precession of the orbital plane that adds a characteristic modulation to the signal. The second stage is merger itself. The moment the 2 event horizons touch and become one, the signal peaks. The third stage is ring down. The newly formed combined black hole vibrates briefly before settling down into a quiescent Kerr state. The exact frequencies and damping times of the ring down are dictated by the mass and spin of the final hole, in a way that the Kerr solution predicts to extraordinary precision. By fitting the entire signal from in spiral through ring down, scientists at LIGO can extract not only the masses and spins of the 2 original holes, but also the mass and spin of the merged remnant. So far, every observed merger fits the Kerr predictions. We have never seen a deviation. The black holes we observe in nature are Kerr black holes, spinning according to Einstein's equations, every single one. Many of those mergers involve fast-rotating black holes. Several involve second-generation black holes that were themselves the product of earlier mergers, born already spinning rapidly, because the orbital angular momentum of their parents went into their final rotation. The Kerr metric, fitted to every observed merger, matches the data. We have not seen a single observation that requires anything beyond Kerr. Astrophysical black holes are Kerr black holes. They rotate exactly as Einstein's theory says they should. So now let us hold the picture in our minds for a moment. The Earth rotates and drags spacetime slightly. The Sun rotates and drags spacetime slightly more. The supermassive black hole at the center of our galaxy rotates at 90% of its theoretical maximum and drags spacetime around itself violently. And there are perhaps 200 billion galaxies in the observable universe, each with 100 billion stars, each of those stars rotating, each of those galaxies hosting a central supermassive black hole that rotates, surrounded by a dark matter halo that rotates, embedded in a cosmic filament whose handedness is non-random. Let me give you some numbers that will help that picture land. The total angular momentum of the Earth's rotation is about 7 times 10 to the 33 joule-seconds. The total angular momentum of the Sun's rotation, despite its larger mass, is less than you might expect, only about 10 to the 41, because the Sun rotates relatively slowly. The total angular momentum of the Milky Way galaxy, including the orbital motion of all its stars, is about 10 to the 67 joule-seconds. The total angular momentum of all the visible matter in the observable universe, if you add up all the rotating planets and stars and galaxies and black holes, has been estimated at around 10 to the 84 joule-seconds. From the spin of a single electron at about 5 times 10 to the minus 35 joule-seconds, to the total spin budget of the cosmos, the range is roughly 120 orders of magnitude. There is no other physical quantity in the universe that spans such an enormous range and yet remains, at every scale, governed by the same simple conservation law. Everywhere in the universe, space-time is being dragged by rotation. Everywhere. The fabric of space that connects you to me, the geometry through which light from distant galaxies travels to reach our eyes, it is being twisted by countless rotations going on at every scale, all the time. The texture of the universe is woven, on a scale we do not usually appreciate, from spin. That observation invites a question. If every level of structure in the universe rotates, and every rotation drags space-time to some degree, then it is at least worth asking, gently, whether the largest level of structure in the universe itself, taken as a whole, might also rotate. It is the next obvious link in the chain, from an electron to a planet to a galaxy to a black hole. The next step up is the universe. And the question, as it turns out, is no longer purely theoretical. The data, in the past few years, has begun to whisper. That whisper is where we are going next. Get a little more comfortable. We are entering the strangest part of the story. Is less than break time equals 1s is greater than number, part 8. Does the universe itself rotate? The cosmological principle, as it has been called since the 1930s, says two things about the universe on the largest scales we can measure. The first is that the universe is homogeneous, meaning that the average density of matter and energy is the same from one place to another. The second is that it is isotropic, meaning that the universe looks the same in every direction. There are no preferred directions. There is no axis along which things are different from any other axis. The universe, on the largest scales, has no orientation. The cosmological principle is the foundational assumption of the standard cosmological model. We call that model lambda CDM lambda for the cosmological constant that drives the universe's accelerating expansion, CDM, for cold dark matter. Lambda CDM takes the cosmological principle as a given, and from there it fits an enormous range of observations with only a handful of parameters: the cosmic microwave background, the distribution of galaxies, the abundance of light elements in the universe, the accelerating expansion. Almost everything we observe in cosmology, lambda CDM, can match to remarkable precision. If the cosmological principle is wrong, if the universe is not actually homogeneous and isotropic on the largest scales, then a large part of modern cosmology becomes wrong with it. The model would need to be replaced, or at least seriously modified, and so cosmologists treat any potential challenge to the cosmological principle with great care and considerable skepticism. They are right too. Which brings us back to where we began tonight, to the JWST finding from February of 2025. Lior Shamir, working at Kansas State University, analyzed 263 galaxies in the James Webb Space Telescope's JADE survey. These are some of the most distant galaxies we have ever imaged. Many of them existed when the universe was less than 1 billion years old, in some cases less than 500 million. Shamir's analysis classified each galaxy by its apparent direction of rotation, clockwise or counterclockwise from our point of view. The result, as I told you in part 1, was a 66 to 34 split in favor of clockwise rotation. The asymmetry grew larger at higher redshift, meaning that the older the universe we are looking at, the more lopsided the distribution. The odds of getting such a result by chance from a universe with no preferred direction were about 1 in a million. Mainstream cosmologists have offered an explanation that does not require any breakdown of the cosmological principle. The Milky Way, like every other galaxy, is itself moving through space relative to the cosmic microwave background. Our motion through the background has a measurable direction and speed, about 370 kilometers per second, in a known direction. Galaxies that are rotating in a way that opposes the line of sight of our motion are very slightly Doppler boosted. Their light is shifted toward the blue end of the spectrum, and they appear slightly brighter than they otherwise would. Brighter galaxies are easier to detect, easier to classify. They make it into the sample at a slightly higher rate than their darker, opposite rotation siblings. The result, the argument goes, is a selection bias. The universe might still be perfectly isotropic. Our observations might just be skewed by our own motion through it. It is a defensible argument. It is the conservative interpretation, and it might be right. But Shamir and others have argued that the bias is too small to explain what is being observed. A Doppler brightness selection of this kind should produce a few percent asymmetry. The observed asymmetry is 16%. The growth of the asymmetry with redshift is also harder to explain by selection alone. A Doppler effect should be roughly constant across the sample, not stronger at greater distances. So there is a third possibility, sitting cautiously in the middle. The universe itself might have a small but real rotation, not fast, not detectable by any direct observation of how the universe as a whole is moving, but enough to imprint a preferred handedness on the spin orientations of galaxies as they form, an imprint that would be more visible at higher redshift when galaxies were younger and their spin was more tightly correlated with whatever conditions in the early universe gave them their initial torques. The number physicists toy with, in this scenario, is something like 1 rotation per 100 trillion years. That is roughly 10,000 times the current age of the universe. It is so slow that no local measurement could detect it. It would not affect the motion of any galaxy in the local universe in any way you could measure with current technology. But across the entire cosmos, integrated over 13.8 billion years, it would leave a fingerprint on the distribution of galaxy spin directions. Exactly the kind of fingerprint Shamir's data appears to show. The JWST asymmetry is not the only anomaly that points in this direction. There are at least 2 others. The first is called the axis of evil. The name was coined by the cosmologists João Magalhães and Kate Land in the mid-2000s. The phenomenon itself was first noticed in data from the Wilkinson Microwave Anisotropy Probe, or WMAP, in 2003 and was confirmed in considerable detail by the Planck satellite in 2013 and again in 2018. The cosmic microwave background, the relic radiation from when the universe was 380,000 years old, faintly glowing at a temperature of about 2.7 Kelvin in every direction we look, is, on average, isotropic. But when you look at its very largest temperature fluctuations, what astronomers call the quadrupole and octopole modes, you find something peculiar. The axes of those modes are aligned. Not perfectly, but to a degree that is statistically uncomfortable. They point in roughly the same direction. And, even more peculiarly, that direction is aligned with the ecliptic plane of our own solar system. The chance of such an alignment occurring randomly is roughly 1 in 1,000. There are conservative interpretations of this finding too. It might be foreground contamination radiation from our own galaxy or our own solar system leaking into the data and producing apparent alignments. It might be a statistical fluke. With enough modes to look at, one of them will look anomalous by sheer luck. But the alignment has survived multiple analyses with multiple instruments by multiple groups over more than 20 years. It has not gone away. And, like the JWST finding, it suggests a preferred direction in the universe. The second additional anomaly is called the cosmic dipole. The distribution of distant quasars and radio galaxies across the sky shows a dipole, a hemispheric asymmetry in number counts. Such a dipole is expected because our own motion through the cosmic microwave background should produce a small one. But the observed dipole, in studies published from 2021 onward, is roughly 4 times larger than that expected motion-induced dipole. The numbers do not match. Either we are moving much faster than the cosmic microwave background dipole suggests, in which case various other measurements are wrong, or the universe has a real anisotropy on the largest scales, in which case the cosmological principle is in trouble. 3 independent anomalies: the JWST galaxy rotation asymmetry, the axis of evil in the CMB, the cosmic dipole in quasars and radio galaxies. Each one, taken alone, is suggestive but inconclusive. Each one has a conservative alternative explanation. None of them, individually, would force a reconsideration of the cosmological principle. But 3 of them, all pointing in a similar direction, are harder to dismiss together than any one of them is alone, and the mathematics has been on the table for almost 80 years. In 1949, The mathematician Kurt Gödel, the same Kurt Gödel whose incompleteness theorems had broken the foundations of mathematics 2 decades earlier, turned his attention to Einstein's theory of relativity. He produced, as a kind of intellectual birthday present for Einstein, an exact solution to the field equations in which the universe rotates as a whole, the Gödel metric. It is mathematically valid. It is a solution to general relativity in the strict and literal sense. And it has properties that are unsettling. Gödel and Einstein were close friends at the Institute for Advanced Study in Princeton. They walked together almost every day. Gödel, who was famously eccentric and suspicious of food and prone to anxiety about almost everything, found in Einstein a friend whose mind moved at his own peculiar speed. They would talk about logic, about mathematics, about physics, about the strange consequences of relativity for the nature of time. Gödel had become convinced, partly from those walks, that there was something deeply unresolved in Einstein's theory about the meaning of past, present, and future. The relativity of simultaneity, the absence of a universal now, had bothered him for years. So when Gödel sat down with the Einstein field equations and looked for a solution in which the universe rotates, he was not engaged in idle puzzling. He was looking for a mathematical demonstration of a worry he had been carrying for a long time. In Gödel's rotating universe, the rotation introduces closed time-like curves. These are paths through space-time that loop back to their starting point in time. An observer who followed such a curve could, in principle, return to their own past. Time travel. Not the kind of speculative time travel that requires exotic matter or quantum tricks. Time travel built into the structure of a rotating cosmos. The mathematics is clean. The implications are not. If Einstein's theory of gravity is correct, and if the universe rotates in the way Gödel imagined, then the past is not a place that is gone forever. It is a place that, in principle, can be revisited. The fact that we apparently cannot revisit it would have to be a contingent fact about our particular cosmological history, not a fundamental restriction of physics. Einstein was unsettled by the result. He never refuted the mathematics. He hoped, instead, that physics would rule it out for some other reason, that the universe would, in nature, turn out to be non-rotating, and the disturbing implications of Gödel's solution would never need to be confronted. To this day, we do not know whether Einstein's hope was well-founded. Current upper limits on the rotation of the universe, from analyses of the CMB and large-scale structure, are extremely tight. The universe can rotate, if at all, no faster than about 1 rotation per 1 trillion years, probably much slower, but the limit is not 0. The mathematics does not require it to be 0. And the JWST data, if it survives further scrutiny, suggests the rotation might not be 0 either. The arbiter, in the next few years, will be the dark energy spectroscopic instrument. DESI is currently mapping the rotations of more than 10 million galaxies in the local universe. If the universe truly imprints a preferred handedness on galaxy spin directions, DESI will see it cleanly. If JWST is showing us a selection effect, DESI will rule it out. Either way, we are about to get an answer to a question that, until very recently, was not even considered a scientific question. We are about to find out whether the universe rotates. And if it does, we are forced to ask a follow-up question that is harder than the original. Rotation, after all, was defined in Part 2 as motion against a frame of reference. The Earth rotates relative to the stars. A galaxy rotates relative to its surroundings. A neutron star rotates relative to the inertial frame of distant observers. Rotation, in physics, always requires something to rotate against. A universe that rotates is a universe that has something to rotate with respect to. What could that be? The answer, in the only published framework that takes the question seriously, is that the universe could rotate with respect to something outside of itself, something containing it. A larger cosmos, in which our own universe is a small object, a rotating object. And the model that draws this picture, perhaps the most provocative idea in modern theoretical cosmology, is where we are going next. Is less than break time equals 1s is greater than. Number, Part 9. The universe inside a black hole. The framework was developed beginning around 2010 by a theoretical physicist named Nikodem Popławski, working at the University of New Haven. Popławski's idea is grounded in an extension of Einstein's general relativity called Einstein-Cartangent-Sayama-Kibble theory. The extension was developed independently in the early 20th century by Elie Cartan and later by Dennis Sciama and Tom Kibble. It adds to general relativity a property called torsion, which is sourced not by the energy density of matter, but by its intrinsic angular momentum, its spin. The link is remarkable, given everything we have built up tonight. Einstein-Cartan theory says that the fermion spin we discovered in Part 6, the half-integer quantum spin carried by every electron and every quark in the universe, contributes to the geometry of space-time in a way that the original general relativity does not capture. At ordinary densities, the contribution is negligible. At the densities found inside a collapsing black hole, the contribution becomes enormous. Popławski's calculation, building on this framework, suggests that as matter collapses toward what general relativity would predict as a singularity at the center of a black hole, the torsion contributed by the spins of countless fermions becomes a repulsive force. Strong enough, eventually, to halt the collapse. Strong enough to push the matter back outward. The collapsing matter, in this picture, never reaches a singularity. It rebounds. What happens on the other side of the rebound is the part that earned the theory considerable popular attention. The rebounding matter, behind the event horizon of the black hole, expands into a new, closed, rapidly expanding region of spacetime. From the inside, that expansion would look indistinguishable from a Big Bang. Quantum particle production during the rebound could generate enormous amounts of matter, just as inflationary models propose for our own Big Bang. The result, in this framework, is that every black hole contains within it a new universe. If this picture is correct, and I want to be very clear here, that this is published, peer-reviewed work, but it is by no means the consensus view of modern cosmology. It is a hypothesis that takes extensions of accepted physics and pushes them into speculative territory. Then, our own universe might be a baby universe, born inside a rotating black hole in a larger parent cosmos. The parent black hole would have its own mass, its own spin, its own history, and we, inside our universe, would have inherited a fingerprint of the parent black hole's rotation. That fingerprint is what every anomaly we have discussed tonight might be. The 2-to-1 galaxy spin asymmetry seen by JWST, the axis of evil in the cosmic microwave background, the cosmic dipole in radio galaxies and quasars. In Popławski's framework, none of these are puzzling. They are the natural consequence of being inside something that itself rotates. There is a particularly speculative addendum, which I include here because it sits at the limit of what published physics has been willing to entertain: the handedness of biological molecules. All the amino acids that life on Earth uses are left-handed in their three-dimensional structure. All the sugars in our DNA are right-handed. The origin of this chemical asymmetry, what biologists call chirality, is unresolved. One conservative explanation traces it to a property of the weak nuclear force called parity violation, discovered by the Chinese-American physicist Chien-Shiung Wu in 1957. A more speculative explanation, harder to test but harder also to dismiss, suggests that the universe itself has a fundamental handedness, and that the chemistry of life inherits that handedness as an extremely faint imprint of the universe's own rotation. Whether or not that turns out to be true, the speculation is large in its scope. It draws a thread from the largest possible scale, the cosmos itself, down through galactic rotation, down through chemistry, all the way into the structure of the molecules that compose your body. It is worth pausing on the Wu experiment itself, because it shocked physics when it happened. Up until 1956, physicists believed that the laws of nature were symmetric under parity, that is, under the operation of mirror reflection. If you watched a particle physics experiment, and then watched the same experiment as if reflected in a mirror, you would see the same physics. Wu, working at Columbia University, designed an experiment that tested this assumption for the weak nuclear force. She used cobalt-60 atoms, cooled to nearly absolute zero, aligned by a magnetic field, and watched the direction in which they emitted beta particles. The emission was asymmetric. The cobalt atoms preferred to emit beta particles in one direction over the other. Reflected in a mirror, the experiment would have looked different. The weak force, in other words, knows the difference between left and right. It violates parity. The discovery won the Nobel Prize for Wu's collaborators Li and Yang the following year, though Wu herself, who had performed the actual experiment, was overlooked. The implication of her result was that nature, at the level of the weak force, has a built-in handedness. Whether that handedness extends further into the structure of the universe as a whole is the open question that some cosmologists are still asking. Now, I want to come back to the central thread before we move into our closing part. Whether or not Popławski is right, and as I said, this is speculation, not consensus, the picture he draws is the only one we currently have in which every level of rotation in the cosmos has a single, unified origin. From electron spin to planet rotation to galactic rotation to the spin of the universe itself, in this framework, every turning we have observed traces back to a single primordial source. The chain of inherited rotation that we have been following all night, in this picture, has an end. The chain begins outside of our universe. In the parent, it may turn out to be wrong. The DESI data, in the next few years, will help settle whether the JWST anomaly is real. Whether real or not, the question itself, the question of why the universe is full of rotation, will be sharper for our having taken it this seriously. Sometimes the value of a wild hypothesis is not whether it is correct, but whether it forces you to ask the right question more carefully. And the question Popławski's framework forces, gently and persistently, is the one we set out with at the beginning. Why is there rotation at all? And if there is, where exactly did it come from? Is less than break time equals 1s? Is greater than number, part 10, the wheel that will not stop. We have come a long way tonight. So I want to sit with the whole picture for a moment before we let it go. Start at the bottom, where rotation has no geometric meaning at all, and work back up. An electron, with no measurable size, no surface, no extent in space, carries an intrinsic angular momentum that we call spin. The Stern-Gerlach experiment showed it in 1922, with silver atoms splitting into two distinct spots on a detector screen. Pauli named it. Dirac, in 1928, derived it from first principles. Making relativity and quantum mechanics fit together required the existence of spin and antimatter as well, as a kind of bonus inheritance. The electron must be rotated through 720 degrees to return to its original quantum state, not 360. The geometry of ordinary space is amended to permit it. And the entirety of solid matter, your body, the chair you sit in, every object you have ever touched, owes its solidity to the spin of those electrons and to the Pauli exclusion principle that follows from it. Rotation is what makes matter possible. Build up. An atom holds its shape because of the spins of its electrons. A molecule holds its shape because of the arrangement of those atoms. Solid matter exists at all because the rotation that hides inside every fermion forces the matter to take up space. Build further. A planet rotates because the cloud of gas and dust that condensed to form it was already rotating, and gravity collapsed that cloud by a large factor, and conservation of angular momentum took the rotation that was already there and amplified it. The Earth's 24-hour spin is not decoration. It is the engine of habitability. Without it, there would be no Coriolis force, no global wind patterns, no global ocean currents, no jet streams, no monsoons, no weather as we know it. The same is true for almost every other planet in our solar system. The two exceptions, Venus, rotating backward, Uranus, rolling on its side, are the result of catastrophic collisions that locally rearrange the angular momentum, even as the total angular momentum of the solar system as a whole was carefully preserved. Build further. A star rotates because the cloud that birthed it rotated. The Sun completes one rotation about every 27 days. A dying star, collapsing its iron core down by a factor of 100 million, can wind itself up into a neutron star spinning 43,000 times a minute, its equator skimming a quarter the speed of light. The fastest pulsar we have ever measured, PSR J1748, is doing exactly that, in a globular cluster 18,000 light-years from Earth. Right now, as you listen, the same conservation law that makes a figure skater speed up is responsible. No special pulsar physics, just the law, taken seriously, applied to the most extreme collapse in nature. Build further. A galaxy rotates because in the very early universe, tiny density irregularities, quantum fluctuations, stretched to cosmic size by the inflation of the universe in its first moments, were tidally torqued by neighboring irregularities. The torquing built up linearly with cosmic time until each region reached turnaround and began to collapse. The collapse conserved the angular momentum that had accumulated. Dark matter halos formed, rotating with a remarkably universal spin parameter. Gas fell into them and settled, by conservation of angular momentum, into rotating disks. The disks became visible as galaxies. The Milky Way is one. Our Sun is on its 20th lap around the center, having taken 225 million years per lap. The dinosaurs lived through less than one. Build further. A black hole rotates because everything that ever fell into it carried angular momentum with it, and a black hole, by definition, does not let what falls in come back out. The Kerr metric, written down in 1963 by Roy Kerr, describes the rotating geometry. Around every rotating black hole sits an ergosphere, in which space itself is dragged. Frame dragging warps the local geometry. The Penrose process, in principle, can extract up to 29% of a maximally rotating black hole's mass energy. The supermassive black hole, at the center of our own galaxy, is rotating at about 90% of its theoretical maximum. The 200-plus mergers, observed by LIGO and Virgo and CAGRA through 2025, all confirm the Kerr geometry to extraordinary precision. Black holes are not just spinning. They are space-time itself made to spin. Build further, one more step. The universe might rotate. 3 independent lines of evidence: the JWST galaxy rotation asymmetry, the axis of evil in the cosmic microwave background, the cosmic dipole in quasars and radio galaxies, all whisper, faintly, that the universe might have a preferred direction. Gödel showed in 1949 that a rotating universe is mathematically allowed by Einstein's general relativity. The current observational upper limit on cosmic rotation is extraordinarily tight, but it is not zero. DESI, in the next few years, will tell us whether the JWST anomaly is real or a selection artifact. If it is real, we will be forced to ask what our universe rotates with respect to. The only published framework that takes this question seriously, Popławski's Einstein-Cartan extension, suggests that we rotate with respect to a parent universe in which our cosmos sits inside a black hole. The handedness of biological molecules, in this picture, becomes a remote inheritance of that same rotation. Whether or not the parent universe picture turns out to be right, the chain we have traced tonight has a remarkable shape. From the smallest possible thing in the universe to the largest possible thing, rotation is everywhere. It is conserved at every step. It is inherited at every step. And the question of where the original rotation came from, the question that we have been gently pushing back, link by link, all night, finds no clean answer inside the universe we can observe. The answer might lie outside of it. The answer might be a fact about the universe that we simply have to accept, in the same way we accept that the universe has matter in it. Or, the answer might be something we have not yet imagined. Here is the thought I want to leave you with as the late hour settles in around us. The universe, in everything we have looked at tonight, prefers motion to stillness. Stillness, at every scale, turns out to be the rare condition. Matter does not sit. Space does not sit. The smallest particle in nature carries an irreducible angular momentum that cannot be removed. The largest structure in nature, if the JWST data hold up, may turn out to do the same. In between, every object we have looked at, every planet, every star, every galaxy, every black hole rotates. The conservation law that ties it all together is one of the few principles of physics that has never failed an experimental test. It is rooted in the simple fact that space looks the same in every direction. The universe, in some way that we still do not fully understand, is built around the idea of turning. Perhaps what we have been calling matter and space and time, and treating as the basic ingredients of reality, are not the basic ingredients at all. Perhaps they are the local appearances of something simpler and stranger underneath. A single, ceaseless, universal turning. A wheel that began before the Big Bang, if there was a before. A wheel we are riding right now, on a planet rotating once a day, around a star rotating once a month, around a galaxy whose lap takes 225 million years, around perhaps a universe whose own rotation we are only now beginning to detect. A wheel that has never stopped. A wheel that will not stop. Good night.